Noise in a sensor is generally everything but the signal of interest. Now, there are various ways that noise can be introduced to your sensed signal. If I have a sensor defined by this box, and I have my signal of interest, and that could be a force, it could be a pressure, it could be whatever I'm trying to measure, a temperature, acceleration, etc. One place that noise can come into the circuit is right here, and I'm going to call that noise source 1, and I'll define that a little more completely later. And so the signal plus this noise from here goes into the sensor, and then coming out of the sensor, so maybe the sensor is converting a light to a voltage or an acceleration to a capacitance. After that, I can have even more noise coupled in to my signal, and that's even before it goes to any kind of signal conditioning circuitry that I might have. So this would be my output from my sensor, and that could be something like a current, could be a voltage, a capacitance or resistance, etc. So that signal, remember, could be something like a temperature, a pressure, force, whatever it is I'm trying to sense. Those are just a couple examples. Okay, so this first noise source that comes into this with the signal, right? So it should ultimately kind of have units with the signal units here. And that could be due to a variety of other things going on in my environment. So if I'm trying to measure an acceleration, for example, if I have some vibrations from an HVAC system, or if I have cars driving by, right, those vibrations might get coupled in to my sensor, and I might actually be measuring accelerations from those vibrations instead of the vibrations that I'm actually interested in measuring the acceleration on. So that would be an example of this first noise type that I might have in my sensor. Noise 2 can have far more sources for that kind of noise. So this could be cross sensitivity to other sense signals. Very common one might be temperature sensitivity. So for example, in a strain sensor, if the temperature changes, that looks like a strain is being applied when a strain might not be actually being applied. So that would affect my output resistance here, but it's not necessarily some random strain that's showing up in my signal. So it is showing up as noise 2 here. I can also have noise coupled in from other sources. That could be like the 60 hertz noise that you might be familiar with, or flicker from fluorescent lights often shows up at somewhere around 35 to 40 kilohertz as well. And I can also have just noise that's inherent to the sensors themselves or other sensor components that might be part of that sensor. And that could be things like thermal noise that would show up, for example, in a resistive sensor, capacitive sensor, any sensor that's operating above 0 Kelvin is going to have some thermal noise associated with it. There are various types of noise as well, and this might influence how you handle the noise in your circuit. One very common type is white noise, and this is a random noise signal with a flat power spectrum. So if I have watts per power per frequency plotted, I'd effectively get a flat line here. So white noise is random. Another very common type of noise showing up in a sensing circuit is Nyquist-Johnson noise. And this comes from thermal agitation of charge carriers regardless of any applied voltage that you might have in the circuit. So a very common example of that for our resistive sensors. If you have a resistor with resistance R, then I can effectively consider that a resistive sensor with resistance R in series with a noise source Vn with a bar over it, kind of indicating a mean noise level. And Vn squared would be defined by 4 kBTR times delta F. So Kb is my Boltzmann's constant, which is 1.38 times 10 to the minus 23 joules per Kelvin. T here is obviously the temperature that I'm operating at. R is the resistance of my sensor. And delta F is the bandwidth that I'm operating over. So this noise, for example, will show up in any resistive sensor that you have. Another particularly interesting noise source, and there are many more that I'm not going through, but this is interesting for sensors, is shot noise. This is due to the discrete nature of current, of charge carriers, of current in a conductor, or of photons in an image sensor. So if you have a camera and there's some noise associated with that, some of that is going to be shot noise. Right? In addition to basic metrics that we have, like in this case, this VN that we talked about for the Nyquist-Johnson noise was the RMS noise, voltage noise on the sensor. So RMS, remember, stands for root mean square. And that might be one metric that we use to quantify the amount of noise in our system. Another metric that is equally of importance to us when we're trying to actually measure a sense signal is also looking at the signal-to-noise ratio, or often called SNR. So this SNR is going to be often defined in dB, so I'm going to have my 20 log base 10 of my signal amplitude, or kind of the RMS version of my signal, over the noise that I have. And that ends up in dB. So for example, if I had a signal value that was approximately 10 times the noise level in my system, so then maybe this is my voltage of my signal, my RMS voltage of my signal was 10 times the noise voltage that I'd have, then I would have an SNR equal to 20 dB. Because I'd have a factor of 10 here, log base 10 of 10 is 1 times 20 in dB. Now, typical metrics for what you would actually want for your SNR is an SNR greater than 3, and that's the straight up magnitude, the straight up ratio of signal over noise. So I'd want my RMS signal value to be about 3 times my noise value. Another one would be 10, and that would be our 20 dB that we just looked at. So these are two fairly common ones. If you really want a robust system, making sure that your signal is at least 10 times higher than your noise floor is a good rule of thumb. But 3 is generally sufficient for most of the things that you'd want to do.